last class, the quasi-periodic route to chaos. Yes, how quasi-periodic behavior can lead to the formation of chaotic behavior. Okay, so what we discussed last class, I just want to recall for around 5 minutes. Let's see. Yeah, I told you why suddenly we started discussing two-dimensional maps. Okay, started discussing about two-dimensional maps because you will not see that is the Nemaxeka bifurcation in 1D maps. Therefore, why we can't see the Nemaxeka bifurcation in one-dimensional maps? Because the formation of the occurrence of Nemaxeka bifurcation needs complex conjugate eigenvalues crossing the unit circle with unit magnitude. And if you have A plus IB, then there should be A minus IB, the conjugate part, isn't it? So therefore, in one-dimensional map, how many eigenvalues you can have? One. So there is no chance of having a complex conjugate eigenvalue, isn't it? So therefore, you cannot have a partner in crime. Yes. So therefore, you cannot have this bifurcation in 1D maps. So where it can be possible if you increase the dimension by one more, isn't it? By increasing the dimension by one, what you do, you have now the possibility of presence of complex conjugate eigenvalues. So now you can have lambda 1 A plus IB and lambda 2 is A minus IB, that is complex conjugate. Okay, lambda 1, lambda 2 are complex conjugates, and as you vary parameters, the magnitude of the eigenvalue cross the unit circle in complex sense, leading to the formation of a Nemaxeka bifurcation. Okay, now what happens after you go through a Nemaxeka bifurcation? I told you, if you see complex eigenvalues, it should come to your mind that something is rotating, isn't it? Something is rotating. So if it is rotating, it will create a closed curve. Okay. So I will give you a nice idea. If you see, I think I gave you an assignment, right? How to do plot the quasi-periodic orbit in Henon map. Did you do? You did, no? I will check up. So you have this fixed point, and then if you observe the closed invariant curve, okay, then you will see, if you don't discard the transients, you will see a magnificent structure. Transient gives you a very nice behavior. How leading you to understand how this closed invariant curve magically occurred. Yes. So if you don't discard transient, you will see something like this. And if you consider more, it will be more even. So you can see that each trajectory is leading to that spiraling thing, and that you observe for the presence of complex conjugate eigenvalues, spiral-like behavior. Okay, fine. So then we discussed Henon map has two parameters. How using those two parameters can we understand the behavior of this map, isn't it? So this is a very nice computational technique one can adopt. So there are two parameters in the Henon. There are two parameters. So what we do A and B, as you can see, just fix the starting and end point of parameter A and the starting and end point of parameter B, okay, on the y-axis. Then we find grid, 1000 cross 1000 grid. Okay. So what you will have around 1000 cross 1000 points, and each of those points as you already know, it will converge either to a fixed or to a periodic orbit or to a chaotic attractor or to a closed invariant curve, or maybe diverging to infinity. Lot of possible behaviors. That's what dynamical systems does. Okay. So what I do computationally, nothing but as you have learned in data, what I do I just take a fixed point. If it is converging to a fixed point, mark with this tile color. Okay. And if it is periodic, mark it with red. and if it is chaos marked in black, then you see this very nice structure, and this gives you the route to chaos. What is the route to chaos? Can you see here? If suppose in your exam you get this figure. Suppose in your exam you get this figure, and one particular direction is being asked, like suppose this is the direction. It is asked like you are going from A to B, in the direction of A to B. Fine. Now, okay, what can you interpret from this route? So if you are going from A to B, what is varying and what is constant? If you are going from the path, maybe not A to B is not a right thing to do. Maybe I'll change my notation. Okay. So maybe I will say this direction, just this direction. Okay. So in this direction, what do you think is constant and what do you think is changing? Any ideas? So you can see if you are going along this path, okay, then right, A is just the constant, same value, but B is changing. B is changing, like B is changing every time. So now you can say if you keep the parameter going to the fixed point, it is undergoing period doubling bifurcation. Therefore, you have this periodic orbit. From here, you went to here. From here to here, what kind of bifurcation can be? Fixed point to periodic. Period doubling. No other route is there. Doubling. Okay, there are routes, but not if it is just directly orbit, right? Only way is period doubling. Okay. But this color code doesn't tell you what kind of period number it has. Okay? After the period doubling, suddenly it goes to chaos in black. So this is nothing but the period doubling route to chaos. Okay, this is just the period doubling route to chaos. So if I give you this picture and draw this curve, and I'll ask you, what is your interpretation along this direction? Okay, then you should say that this curve gives us a route to the formation of chaos in Hanon map. Okay, and what is that route also you should mention that it is going to take attractor. So it's a usual period doubling route to chaos. Fine. Then you see suddenly that means this is such an interesting phenomena that you see the boundary between periodic behavior and unbounded. Boundary between the periodic orbit and unbounded. Just a fraction or decimal change in the parameter values can suddenly shift your behavior from a nice periodic orbit to unbounded, like the trajectory will just go away. You can see the effect of nonlinearity here. So suppose, can you tell me this value? Suppose it is 0.5 comma minus 3. Okay, then this can be just minus 0.49 comma minus 3, isn't it? And just by the 0.01 change, suddenly red is becoming white. What do you mean by red becoming white? Red was periodic, and when you just change the parameter by 0.0, so it became white. That means it is diverging off to infinity. So that is what this nonlinear things you cannot predict, and this is the beauty of this. Okay, right. So yeah, we learned how it can be chaotic and how quasi-periodic orbit looks like. I would suggest that if you are doing anything related to quasi-periodic orbit, always keep the transient and pause your iteration when you're plotting, so that you will get an idea how the iterates are moving around and creating the plot. Okay. And quasi-periodic orbit to chaos, like you can see that this is ahead of the, this is a bit deep concept. I am not going to that, but quasi-periodic orbit can lead to chaos. Okay. I have not told you, but I'll just tell you, like there is an invisible curve which you do, something known as a critical curve. Okay, something known as a critical curve, LC, ligne critique in French. Okay, and the moment you vary those parameters, of will collide with this ligne critique curve, which is invisible but exists. That's a boundary, invisible boundary. And when it collided there, it started to lose its smoothness. Okay, I think you have seen Venom. Is it? Have you seen Venom movie? So Venom is such a nice structure, isn't it? It is such a nice structure. But when he hears certain frequencies, see how he becomes like all these things are vibrating and all. So that's the condition. Like this is the lignity like that. The curve is like that. So when this closed invariant curve touches this guy, then it started to lose its smoothness. Instead, it will now look as this. So this transformation is there. Okay, this transformation. So you lose smoothness. Nice curve, right? Nice golf club kind of area. But suddenly when it hit this lignocritic curve, which you compute, which I'm not going into detail, okay, I'm just telling you the mechanism, then you will see that it behaves very oddly. It started to lose its smoothness. How it loses its smoothness? A sharp kink here. If you see sharp kink, loss of smoothness. Derivative won't exist there. Slope won't exist. Tangent won't exist. So therefore, like this, it will form this chaotic attractor. That's an idea. And yes, we saw many other things. Why we came to frequencies? We said that every object has an internal frequency. Okay. And when you subject some external force to it, it vibrates with an external frequency. Now, depending on the ratio of the external frequency with the internal frequency, characterize the behavior. Okay. If you see, we discussed two aspects, plus. If the ratio is rational or we say commensurate, it implies a periodic behavior. Okay? If the ratio is irrational or incommensurate, it implies quasi-periodic behavior. Fine. I told you, I just gave you an intuition also that why the rational number, if it is a rational number, it is periodic. Why? Because suppose I told you forget about maps, go to a differential equation case, the flows, 3D flows. So this is the 3D flow, and we are considering x, y, and z axis. Okay, and this is a periodic orbit in continuous system. Okay, in discrete, see discrete points for a periodic orbit, like it goes to here, it goes to here, here, then it comes back again. This is discrete map, right? But this is flow. This is a flow. If you see continuous curve winding around, okay. Now the idea is how can a simple engineering perspective is just place a paper. Just place a paper, okay, in the middle of the curve, okay. What you will see, the trajectory is going like this, hitting, coming outside, going again hitting, again going outside and turning on the original point. So how many times it crossed the paper? 2 times. Okay. So now if you just see this paper and forget about the flow, so it is just a period 2 orbit, isn't it? It is just a period 2 orbit. And the period 2 you are observing in the flow also. It is winding 2 times. So therefore this is the main reason why we started this course with the concept of 1D map. Okay. Because flows, any complicated flows, finally you have to knock the door of the map. Okay. Any flows, if you want to understand, it can be boiled down to a discrete map. Therefore, discrete maps are interesting. Okay. Anyway, so this is the Poincare section. The paper is nothing but this idea Poincare did, so it was known as a Poincare section. Fine. So, and I also told you that if you see this fraction like 4/6, Suppose the fraction is 4 by 6. You have to reduce it to the simplest way possible. Like if it is 4 by 6, you have to do it 2 by 3. So what this 2 by 3 means, I also conveyed you one very important concept, that any ratio, any frequency ratio, that is f2 by f1, can be thought of as a motion on a vada, on a torus. Okay, on a torus. How you can see on a torus? You can see complicated trajectory in red. Trajectory in red. It is following. It is on the torus. It is on the torus. Okay. And now what you do? Put a point in. What you will see? Suppose this is the case. Suppose this is the case. Like the red curve is going. See only the red curve. Now what I do? Put a pointer plane. So what you will see? 2 points. 2 points, isn't it? 2 points. So it's a piece of orbit. But if you see a mesh showed in the previous class, like lot of trajectories are moving together, then if you place it, then you will see on that point circle. Okay, fine. You will see something like a circle. So that is a closed invariant. Okay, so that is a quasi-periodical. Okay? So I told you also that there are two kinds of two kinds. Can you tell me what are the two kinds? One is of course like this. One is of course looking like this. Consists of millions of points. Millions of points. Mind you, this is not a curve. This is not a curve. We say it to be a curve, but this is made. I told you how this curve was made up of. Do you remember? You start from here, iterate, again you land here, here, here. Then next iterate will not come close exactly at this, rather close to this point. Therefore it is known as quasi-period. So to come close to this, this, again this, right? So yeah, you can see that slowly it will build this curve now. But there is a pattern in which it is moving. It is not moving randomly. There is a pattern in which it is moving. So therefore, this is known as a quasi-periodic closed invariant curve. Attractor, it is also an attractor. This is a simple one. This we call it one torus. If you put a 1 here, that means there are two frequencies. Here, that means there are two frequencies. Okay. Fine. But now let us come to the vada. Okay. So you see this vada, like this is a higher dimensional quasi-periodic orbit. This is also a quasi-periodic orbit. Okay. If you see a vada, it is also a quasi-periodic orbit. Maybe. I can show you that vada actually. Maybe like radio physical. I think we can do something like, yeah. Let us see an example from an applied perspective. I think if our ecology student would have been there, he could have found it interesting. But anyway, so I want to show you this. So check this, that this is a bifurcation diagram. This is just a bifurcation diagram I have considered. Why it happened like this? What happened? Change. I cannot go left and right. How I can go right? Huh? So you can see here. Yeah, you can see the bifurcation diagram for this map. This is a 3D map, okay? And what we are doing the bifurcation diagram, I am showing you how the quasi-periodic orbit looks like. So you can see the patterns here, isn't it? It is not chaotic. It is not chaotic. I think if you have seen our bifurcation diagram, you can see, let me turn it on. I will show you our bifurcation diagram from the first. Let us see the bifurcation diagram there. Maybe in our test, or maybe a good one. Yeah, this area doesn't seem to have any patterns. The chaos doesn't seem to have any patterns. Do you see anything on nearby this area, this side? Pattern is there, right? Not much of a pattern is there, but you will see some kind of pattern now, like here. Now compare with this guy. Compare with this guy. You can see something, some kind of some nice behavior going on. Some kind of frequencies rippling. Okay, some kind of behavior is happening. It's not chaotic. So, but it looks exactly like chaotic. It is looking like a mess. So you cannot differentiate between this mess and this mess. This mess is chaos. This mess you are seeing right now is chaos. Okay, but the mess you are seeing here, here, no, it is not chaos. It is quasi-periodic. Okay, so it is often very hard to distinguish between quasi-periodic and chaos. Okay, so therefore there is something known as Lyapunov exponent. We will come to that today. For chaos, Lyapunov exponent is greater than 0, positive. But for quasi-periodic orbit, Lyapunov exponent is 0. That is a characteristic. You can see the Lyapunov exponent is good in getting to 0. Like there are 3. One of them should be 0. One of them, not all of them. One of them. Can you agree that one of them is 0 here? Blue is fully 0. Blue is fully 0 here. And what I am showing in this full interval is all quasi-periodic orbit. Okay. And what I am doing is I am considering 3 different values. Values A, B, C. Okay. A, C, D, E. And I'm showing you the plots. See, this one is the closed invariant curve, isn't it? This one. Very nice structure. And I just showed you. Okay. Then suddenly it went to the Vada. Yeah, this is a very oh yeah. Topologically, it is a Vada, but it is a very slim Vada. Okay, very slim Vada. Hmm? Yeah, and this is a high dimensional torus. This is a torus. Okay, so this is quasi-periodic. This is also quasi-periodic, but it is one torus, 2 frequencies, So it is known as a 2 torus. Why it is 3 frequency? If you put a cross section, you will see a circle. For a circle, you saw there are 2 frequencies. That circle is it only that? No, it is moving. No, that is another frequency involved. It is moving there. So 2 plus 1, 3 frequencies. So therefore, interesting. This guy is something even more interesting. Okay, what is that more interesting? I'll tell you. Here you see the trajectories are hopping in between the two. I will tell you how the case is. Like, let me draw this. How it will be like. So you saw this trajectory to be closed invariant curve, isn't it? So now this is also equivalent to, this is also equivalent. One point is here in 3D space. Okay. Another point is here. Another point is here. The next point is here. Next point is here. But they are making a circle of their own, but traversing each of them disjointly. Can you get the idea? It is hopping like this: 1, then 2, then 3, then again 4, then again 5, then again 6, 7, here 8, again here 9, 10, 11. You see how it is hopping? It is hopping in between 3, and it is mechanically creating a curve in each of them. So this is known as, like, you will see something like this, and this is, you should not interpret this as three different curves. It is just one curve, but due to the hopping nature, it is giving us that feel. So it is known as something like a cyclic uh, closed invariant. You don't need to know, but I'm just telling you, those who are more interested. Okay, fine. So yeah, so like that we came to know, and such kind of frequency locking, actually, you see uh, this moon's motion and Earth. Okay, they are locked. Their behavior is locked. So we on Earth get to see only one side of the moon, and the motion of Mercury about the sun. Both cases are In both cases, tidal force cause an interaction between the axial motion of rotation and orbital motion. The two motions become locked to each other. Each of the motions, see, and they are locked to each other. Therefore, we kind of see one side of the moon. So you can see this goes to solar system is a dynamical system. Solar system is again a dynamical system. In our time scale, it is very uniform, but sadly, solar system is chaotic. Solar system is chaotic. That means after many years, like millions of years, the time scale is million of years. Earth will move out of its trajectory. All planets will move out of their trajectory, and chaotic orbits will be formed. And yeah, we don't. So that's the, and it has been proved. It has been, so yeah. Okay, so this is all about the recap of our previous class. Now we'll start with our fresh new class. Okay, I told you that this class we'll start off with a very new map known as a sine circle map. Sine circle map. Okay, but why again? Why again? We are studying this 1D map. Many of you might be wondering, logistic map sufficient, Anu, huh? Isn't it? Why we need to learn the sine circle map? Okay? Any ideas? Huh? Why we are learning the sine circle? Think about it. If the answer lies in the name. The answer why we are again studying, sine circle map lies in its name. Okay. Any ideas? Someone is okay. Okay. So why are we studying sine circle map? So actually, we learned a lot of concepts last class, like frequency locking. If it is a rational number, it represents a periodic orbit. If it is irrational, it is representing a quasi-periodic orbit. Yes, you got all those ideas. Okay, but the question is, we are just studying it just like theoretical case. We are not seeing it happening. We are not seeing it happening. So this is one such example. This is one such example. Map is a mathematical model. Okay, it's a mathematical model. I won't say it is coming from physical intuition. Okay, but science circle model is a mathematical model, which is a toy model to understand the quasi-periodic route to chaos in a simplest way. So this is the simplest map known till now, which remains hidden in lot of aspects. It does. People are still studying it now. Okay, So it has been but discovered since I don't know, at least not big, yeah, maybe at around 1950s or 1960s. Okay, but still, lot of open problems are still there. So this is known as sine circle map. It's the simplest map to understand, uh, and explore. To understand and explore about quasi-periodic group to chaos. So you can see this. So therefore, we are learning it. Fine. So yeah, and how the iterates of this map, you know that if there is after again and again, right? Like the Hanon map, the map go to next point, so on. But in this sine circle map, how can it iterates? That's the question. So here also there will be points, iterate after iterate as you apply the map. Okay, but this will be thought of as angles on on circle. Okay, so you will have something like this circle map. You start with this theta naught. Suppose this is the base, and this angle is theta naught. Okay, so this point is characterized by the angle. The location of this point is characterized by the angle, isn't it? If you lie at this point, it will be a different angle, no? Yes. So this is theta naught. You apply the map. You apply the map. You go to the next point, theta 1. Apply the map again. Go to the next theta 2 and theta 3, and so on. The motion is happening. Okay. So and you understand how this motion is. That's the aim of the this map. Okay. It will give us lot. It hops in between 2 or 3 points. It can be fixed point. It can just stay there, no movement. It can be chaotic also. Okay. So yeah. So not in many cases, I think, not in many cases. So if you want to understand any aspect, so I will tell you that when you place a Poincare section to a flow, see a curve. Okay, that again, if you see a curve, that can be understood as a circle map again. Okay, but people can say to you that it might not be a perfect circle. It can be of a different shape. Okay, but topologically, it is a circle. Topologically, like what you can do, think this guy as a rubber band, okay, or a thread, and you can pull this on this side, pull this on this side to make it look like a circle. Okay, so still there is no problem. Still we can carry on with the concept of angles. Okay, here. That's the, maybe I can share you this book. Okay, maybe I can share with you the book. It is the book by Hilborn. It's a very nice book, like to understand this. He presents the concepts very intuitively. Hmm? Fine. Fine. So how we write a map? Like now you understood that this is a map which you have the angles, and the angles are keep on iterating the new points. So can you tell me the form, how it should look like? I'm not asking exact form, just like a general form. Just by looking into our previous slide, this one. From theta naught, you go to theta 1. From theta 1, you go to theta 2, and so on. So can you tell me what should be the map in a general way? Suppose the map which takes these points like theta naught to theta 1 is represented by f. Suppose the map which takes the angle theta naught to theta 1 is represented by the map f. Okay. Now, can you tell? I have given you 99% of hints. What should be the, if I say to you to a map, like what's the general form of a map, discrete map? Xn plus 1 is f of xn, isn't it? You put xn as an input to the f iterate, and it iterates and creates this x1 n plus 1. New point xn plus 1. Yes. So can you tell me in this term now? What do you think? Yes. It's a simple one. I'm giving you this. Huh? Yeah. Yeah, tell. Louder. Huh? Huh? One is f of theta naught. Fine. Ah, some very nice things. Okay, it did not happen for a long time. So let us move to next. Okay. So theta n plus, yeah, what he told is uh, theta 1. Yes, theta 1 is f of theta naught, right? Yes, theta 1 is f of theta naught, but that's just one part. How can you write general? Yes, 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 that's it. So general form is theta n plus 1 is f of theta n. Exactly, exactly. So you state theta n, apply the circle map, f, what how it looks, okay, and you go to the next angle theta n plus 1. You do it continuously and analyze the behavior, okay? Fine. So this is the definition, and depending on the map f, circle map or a sine circle map. So actually we will see these two kinds of map actually. These are two different maps. Okay, what is a circle map and what is a sine circle map? Okay. So what is a circle map? Any ideas? So usually you should we should make some notation. Make some notation. I told you that you have a circle like this. This is the baseline. Okay. Theta naught. This is theta naught. Okay. Then you move to next angle theta 1. You move to next angle theta 2 and so on. Theta 3. Fine. Okay. So now you should think that, sir, it can cover a full circle. No. If it starts, it can cover a full circle by 2 pi. 2 pi is the angle, like the full angle. And if it starts again, what you will say 3 pi? You will say 2 pi. So suppose this guy transferred like this. Here. So here it is 2 pi. It is making a 2 pi angle now. Again, if it went somewhere here, or maybe here, say theta 8. So, or 3 pi plus any ideas how it should be? That will work, no? That will work. But this is confusing. This is confusing. You have to monitor the angles again and again. Okay. So therefore, how about instead of dealing with angles, we will normalize it. We will normalize it. Okay. If it is starting from 0, it is 0. That is 0 by 2 pi. We divide it by 2 pi to normalize it. And if it is reaching 2 pi, then we will do 2 pi divided by 2 pi. So it is 1. This is 0, 1. So you can see that now your angles will only lie in between 0 and 1. Isn't it? Formula is like this. Your angles will always lie in between 0 and 1. Okay. Got it? If it is in between 0 to 2 pi. Yes. But yes, if it moves more than that, we have to take care of it. How we can take care of it? Yeah. So I will write a model which takes care of that. You think how intelligently they have thought about this. So this is known as a circle map. This is known as, and this is denoted by this theta n plus 1, which is equals to f of theta n. This is equals to theta n plus some omega mod 1. Okay. So you are getting what I've written it here. So this part you already knew. Now I am telling you what f of theta n looks like. It is just a linear function. It is just a linear function theta n plus omega. So can you understand how the map is behaving? It is very nice. It is very nice. Can you tell me the dynamics of the map just by looking into, draw a circle, maybe a bigger circle. Suppose a bigger circle. Sorry. Suppose a bigger circle. Okay. And you have a baseline. This is 0 degree. Okay. Now suppose you have condition which made theta naught. Point. This is maybe theta naught. Okay. Now, can you tell me what should be the next iterate depending on this form of equation, this map? So next point should be theta 1 equals to omega, but mod 1. But mod 1. Because omega can be any number. Omega can shift the angle to any number, isn't it? Yeah. Why not? It's mod 1. Oh, okay. I did not tell that. Okay. What is okay, okay. 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 What is mod 1? What here? That's what I told. Yes, what is mod 1? Suppose I told you that it made already a 2 pi circle. Okay, is 2 pi? Yes, it is 2 pi. Why? Because it's this is 2 pi, isn't it? Why? You started from here, now you enter the same domain again. How much degree it made angle? 2 pi. Think of this like this. It is going and making that angle full angle. Now instead of stopping there, you are moving more here. So what angle it moved? Calculate it, right? What you are calculating? 2 pi plus some angle again. Yes, that is confusing. That is confusing. It made a very tiny angle. What if it made more angles? Some 3-4 loops. It is therefore we made this concept of mod 1. Okay, what is the concept of mod 1? We said first normalize. We will normalize. That means angle from 0 to 2 pi, any angle from 0 to 2 pi will now look like 0 to 1. How? This is normalization. Divided by 2 pi. Divided by the total interval. Okay, this is normalization. I think you also learned the normalization in data analytics also, no? If you see very high price, you boil it down to some like lowest number you can do. So this is what the normalization looks. So instead of denoting the angles like pi, 2 pi, 3 pi, you will denote by numbers. 0, 0.5. If it is 0.5, what does it mean? Yes, pi by 2. If it is 1, it should mean 2 pi. Yeah, you are dividing by 2 pi, right? If it is 1 and you are dividing by 2 pi, it is 1, then the numerator should be 2 pi. So the angle should be 2 pi, like that. If it is 0, it is 0. It is at 0. 0 by 2 pi, 0. Okay. So this is going from 0 to 1, but it can go to 1.5 also, isn't it? Because if you increase the angle, 3 pi divided by 2 pi, what is it? 1.5. Suppose it made a 3 pi angle and you're normalizing it, what it should be? 1.5. 1.5, isn't it? So then you can see that as you increase the, there are chances that this will go to unnecessary diverging behaviors. The number keeps on increasing. Therefore, what the researchers thought is we will only deal in between 0 to 1. The dynamics will only be concentrated in between 0 and 1. How you do it? That means if you say 1.5 mod 1, okay, then the answer will be 1. Sorry, 0.5, yeah, 0.5. Okay. What it does, it divides by 1, you take the remainder. It divides by 1, you take the remainder. What is 1 divided by 1.5? 1 1 is 1.0, you minus it, 0.5. Isn't it? Isn't it? So therefore, 1.5 is nothing but 0.5. 1.5 mod 1 is nothing but 0.5. Are you getting it? Let us do some exercise. Okay. So I told you theta n plus 1. Let us keep the map. Theta n plus omega mod 1. Fine. This is our circle map. And we are learning this map. Okay. Now I'm telling you that if you started from here, made a circle loop, okay, and you go like this, okay, it's very confusing to calculate this angle. How much angle did it make? It is confusing a bit. So therefore, instead of computing the angle, we talked normalize angles. Normalize the angle. How you normalize the angle? So you have 0 to 2 pi. They said that we will fix the starting point. We will fix the starting point to be 0, final point to be 2 pi. Okay, final point to be 2 pi. And we normalize it. How you normalize? You divide by the total interval, that is 2 pi. So what it should give? 0, 0 to 1. Maybe you can come here. Maybe you can come here. You can come here. It's also there. If you want to be very front, you can take it. Yeah, so now you can understand that. Now you can understand that 0 to 2 pi is nothing but in between 0 to 1. It is just in between 0 to 1. Okay, now if I tell you rotations, can you see that what is meant by 1 rotation and what is meant by 1.5 rotations? If it is 1.5 rotation, it is just like 0.5 rotations. Isn't it? Do you understand? See how 1.5 rotation looks like. Let us see. This is 1 rotation. Okay, agreed? Agreed, this is 1 rotation. Let us do 1 more rotation. Half rotation. Okay, this is half rotation. Now, instead of doing that, why not? Instead of treating it as 1.5 rotation, why not we just think that it is just similar to this guy? Isn't it? What do you think? Is it similar? Do you agree? Confusion. Huh? What I am telling is instead of see 1 rotation it already made, no? So why we need to consider it? Okay, it is started newly for the half rotation. So it is just like you start from 0 to again that half angle. It is just similar. So here you did 1.5 rotation, which is just similar to 0.5. And mathematically, you can think that 1.5 mod 1. This is just like 1.5 mod 1 is giving you this. What is 1.5 mod 1? It is nothing but mod is nothing but modulo. Modulo is nothing but remainder. Sorry. Modulo is nothing but remainder. Okay. What is the remainder? If you divide it, the residual is the remainder. So 1.5 modulo 1. 1.5 modulo 1 means that you are dividing 1.5 by 1. So 1 times what you will do? 1. Isn't it? You have 1 here. Then you minus it. So it is 0.5. This is the residual and this is the remainder. Okay. So therefore, if you see 1.5, it is nothing but equivalent to 0.5 rotations. Okay. This is the meaning. Why we do this? Always the dynamics will be in between. It will not escape 1. That is the main reason we are doing this. Okay. Else, it will just keep on adding 1.5, 2.5, 100.5, 1000.5. Okay, so not make any sense. Okay, so now how this angle looks like? Can you tell me how the dynamics looks like for this map? Theta n plus omega mod 1. This is the circle map. Let us understand how. So what should be, suppose theta naught you started. What should be theta 1? Theta naught plus omega. Okay, theta naught plus omega, but the result should be mod 1. The result should be mod 1. Okay, it should be mod 1. I will not write it again and again. Okay, but it is implied. If I write theta naught plus omega, it is implied that the result is mod 1 operation already done. What should be theta 2? Theta 1 plus omega. Again, yeah, mod 1. So similarly, any guy you consider theta n, that is theta n plus omega. Okay, mod 1. So how this is mathematically we have written all this. Okay. Now I am asking, can you interpret this in terms of the circle? In terms of the circle, like this is the base angle. Okay, this is the base angle that is 0 degree. Base angle that is 0 degrees, and you have this is the initial point. Theta naught is the initial point, that is the making theta naught degrees. Okay. Now I'm asking you, sir. Now I'm asking you that what should be the next iteration? Next iteration should be theta 1, that is theta naught plus omega. So what you are doing? You are adding omega to theta naught angle. So it should shift, right? The angle should shift. Previously it was theta naught. Now it should be, guy should be omega. So this full angle, theta plus omega, isn't it? Agreed? This should be the new point, theta 1. Any issues? Is it clear? Okay. Omega is less actually here. Omega just got less. Therefore, we did not worry about mod 1. Okay. Now, if suppose omega was around maybe 2 pi, omega was 2 pi, what it should be, or 3 pi, what it should be, let us consider 3 pi. Let us consider 3 pi just to have an intuition. So, yeah. So this is the 0 degree. Suppose this is theta naught. Okay. Now omega is say how much? 3 pi. Let us do omega equal to 3 pi. So this guy should be rotated by 3 pi, right? So what is 3 pi? Consider this is 2 pi. Up to here it is 2 pi. And from here again it goes till here. Sorry, it goes till here. That will be 3 pi. Okay. This will be the 3 pi angle now. So the new point theta 1 will be here. What do you think? Ideas. So I'm just giving you an intuition how the circle is moving. Okay, how the points are moving on the circle. Okay, so actually we will not deal with this circle anymore. Actually, we don't want to deal with this circle because now you see how much effort you are putting to understand where the angle went, how much angle it did, and all this. Instead of that, an easier interpretation is just plot theta n plus 1 and 0 to 1. This guy is also going from 0 to 1. Normalized version. This is the normalized version. What will happen? Suppose you started from here. This is theta naught, isn't it? You started from here. What is happening? You go to the next point. Suppose here. Okay, next point, so on. Increase, keep it on increasing. Then you hit one, then it will have a tendency to increase more than one. Okay, it will have a tendency to increase more than one. But can it increase more than one? Because of modulus, what will happen? Suppose 1.1 it became. Then due to the mod 1, what will be the output of this? 0.1. Eliminate, just take the decimal. If you apply the mod 1, just take the decimal point. So if it is 2.1, what is 2.1 mod 1? Eliminate 2, that is just 0.1. What is 2.3 mod 1? 0.3. Is it? What do you think? Think about. Okay, anyway, let us not make it complicated. Let us be back. Okay. So you increase, this is theta naught, keep on increasing, it will increase one. It cannot increase more than that. Now it will be forced to move down. Okay, so it will be forced to move down. The moment it hit 1, okay, it will be, if it is 1.1, it will be forced to move here. 0. Now you can see this will be 0.1 around. 0.1. Now again it will start. Okay, so you now know how the function looks like. How the function looks like. You will see the function like this. Like it is linear because it will be linear because this is a linear function. This is a linear function. Ink range. But this is the, yeah. So this is the linear function. This is a straight line. It has to be straight line. Okay. The angle will increase linearly, isn't it? Do you agree to my statement that angle will increase? Angle will vary. Am I correct? Why? Because theta n plus 1 is varying just theta n plus omega linearly. If I had done theta n plus 1 is theta n square, plus omega theta n mod 1, then it is a non-linear map. Now you are dealing with a linear function here. So it is a linear dynamics. Okay, it is a linear map. You see the function to be linear here. Lines. Straight lines. Okay. Just straight lines. Agree? Agreed? Fine till now? So let us define some more aspects on this. So this is how the function looks, how the linear function looks. This is the mapping for theta n plus 1 is equals to theta n plus omega mod 1, the circle map. Circle mapping. Okay. One good question for you to do or explore is, can this map show chaos? Can this map show chaos? It might be tempting to think that since it is a linear function, it might not show chaos. But I want you to think more about it because it is not a smooth function. It is not a smooth function. How was logistic map? How was logistic map? Do you remember logistic map? So if you plot xn and xn plus 1, hump, you'll get like a hump. That was a continuous function. Okay. And you saw chaos here. And it was a non-linear function, non-linear. But now here, it is a linear function. But you see that you your pen again to draw this next part. You should think whether this is continuous. Yes. So whether it shows chaos. Think about and let me know. This is an assignment for the next class. Okay. What is the assignment for next class? can this map show chaos? Chaos. This circle map, theta n plus 1 is equal to theta n plus omega mod 1. Can this circle map show chaos? Let me know. What you can do, maybe try with bifurcation diagrams. You can try with bifurcation diagrams. Draw the bifurcation diagram. Do you see any period doubling root to chaos? Do you see no period doubling root? Whatever you do. See, it is a very easy thing. It is a very easy thing. Only one parameter you have. Theta versus omega you have to plot. Isn't it? Omega is the parameter, right? Omega is the parameter, isn't it? Depending on the parameter you are changing it. Think about this. Can this 1D map show chaos? Circle map. Okay. Let us think into something more about this simple circle map. Okay. So, winding number. That means, I think you must have, how many of you have heard about winding number or rotation number? Winding number means, you see the circle map, it is winding. No? It is making a coil, like a copper coil. So how the circle map moves? You start from here, go like this, come to this guy, might not stop there, go again, maybe go again, maybe here, you stop, maybe here. Yes. So this can be the dynamics of the circle map. Okay. Yeah, the modulus is. But I'm telling like the points can lie, like this is the original motion. This is the original motion, but the mod 1 motion you can explain. Okay. No, you were not there when I was discussing that. If you angles, you normalize it. Normalize means divide by 2 pi. So you are in between 0 to 1 now. Okay, that's the idea. But here I am showing you the circle, the angles. Okay. Fine. So there is a new definition to understand this winding, to understand how much it winds itself. There is something known as a winding number. Okay, winding number. Or maybe you can also call it as a rotational number, rotation number. Winding number or rotation number. Okay. So what it does, can you see the mapping for the circle map? Mod 1. Yes, this circle map. Now, the idea is, yes, the idea is, should be the idea. Idea is, to understand about winding number, first step is start from an initial condition. Start from an initial condition. What should be the initial condition? Cannot. Initial angle. Then second point is keep iterating the map. Iterating the map. If you keep iterating the map, what you will get? If you keep on iterating the map, what you will get? Suppose n times, what you will get? No, Fn, that like the circle map, like in terms of function, Fn of theta naught. Yeah, we'll later solve it cleanly, but I'm writing in general now. So Fn of theta naught, isn't it? After n steps. Yes. But here, without taking mod 1. Here, without taking mod 1. This is something important. In order to compute winding number, we have to proceed without using mod 1. Okay. So start from an initial condition theta naught. Then second is keep iterating the map n times, that is Fn of theta naught. Keep iterating, but don't use mod 1. Here, don't use mod 1. Okay. Then you know the angle will keep on increasing more than 2 pi, 3 pi, 4 pi, 6 pi, like that without 2 pi modulus. Okay, fine. This is something interesting. Then this winding number, then the winding number is defined as definition. Okay, this is the definition. So we call it to be like this omega. Okay, this omega. I think there are two types of omega. One is little omega, one is big omega. Okay. So you know this is also omega and this is omega. So we will see which one is little, which one is big. Yes, something like this. So you have similarly theta. This is small theta, this is big theta. This is small theta and this is big theta. Sigma also. This is small sigma, this is big sigma. Is there a big lambda? I don't know. Pi also, small pi, big pi. Huh? So like that, mathematicians have been like surviving on these notations. Okay, but anyway, this omega, that is the winding number, is defined as Fn of theta naught. How many rotations it did after n iterations minus, so final point minus the starting point. This is the final point, Fn of theta naught minus the starting point. What is the starting point? Theta naught. And you take the average. That is n, because you did n number of iterations. Okay, so this is the winding number definition. How much amount you winded yourself? So after n number of iterations, you started from theta naught, you go to Fn of theta naught, subtract it from the initial point, that is theta naught, then divide it by n. Agree? Okay, so but this is the definition we have taken. Okay, this is just the definition. But keep in mind that we are not taking mod 1. We are not taking mod 1 in the definition of winding numbers. So Fn plus Fn theta naught can be 3 pi or can be more than 1. Because you are normalizing it. So it can be more than 1. For 6 pi, it is 3. For 6 pi divided by 2 pi, it is 3. Okay. 3 minus 0, how many number of iteration? So you can believe that it will be like a fraction kind of thing. Some kind of fraction. Okay. I'm not saying whether it is rational, irrational, anything like that. It will be a fraction. Fine. So why actually we added this? Why no mod 1? So actually it is in the book that this limit, like this is not the actual definition. We have to take the limit actually. You can answer, I can go for infinite number of iterations. I can go for 1 lakh iteration. I can go for 1 crore of iterations. Millions, billions of iterations. But then we have to say something, right? So then actual definition is, if you take the limit n tends to infinity, Fn of theta naught minus theta naught by, why we take the limit n tends to infinity? Think in terms of the dynamics. Yeah, n is increasing, but why we are, what I mean by here is, I am not bothered about low values of n. I'm not bothered about low values of n. What is n? What is small n? Iterations. That is the Fn, right? If n equals to 2, you are doing 2 iterations. So I am only worried about a large value of n. If I want to compute winding number, I am only interested in large values of iterations. Okay. So this limit n tends to infinity signifies that leave away transients. Leave away the transients. Okay, you discard transients. I am not worried about transients. This is the main reason of considering limit n tends to infinity. Transient means, I told you, transient means, so you plotted the Hannon map, chaotic attractor. Did you discuss transient in that case? Yeah, that's what you are missing it. So what I tell you, when you plot the Hannon map, when you plot the chaotic attractor of Hannon map, This is the XY plane. This is the XY plane, isn't it? What you do? What you do? You start from any initial guess, go to next point, go to next point. It will hop randomly somewhere like here. Then slowly it will form this pattern. It will start forming this pattern, isn't it? Which one did you see? You saw this one. You saw this one, right? So, but these guys also existed, right? Also existed. But if you keep on these guys, then you cannot visualize this properly. These are actually the transients we consider in nonlinear systems. In nonlinear maps, it is like that. Like before converging to an attractor, it will take some steps. Before converging to an attractor, it takes some steps. Why it takes some steps? Why it takes some steps? So it depends on your initial guess. It depends on your initial guess. Suppose you started from here, right? Suppose you started from here. Do you agree that the distance is a bit more from the chaotic attractor? This is the chaotic attractor, right? This is the chaotic attractor here. This is your initial condition. This is your initial condition, isn't it? Now, how you can expect that magically go to the chaotic attractor? It will take some steps, right? It will take some steps, isn't it? So how it will take some steps? It will go like this. It will try to go to the chaotic attractor. It will find a way. Okay. So slowly it will converge here and then start iterating and converge to chaotic attractor. So the moment it goes from initial condition to chaotic attractor is the transient. That you have to discard. Now consider another initial condition. Maybe here. This is the initial condition. Can you see now the distance is very close? So the transient will be very less or negligible. Now you get the idea of transient, why the transient is always there and we have to discard it. Because the initial condition, see, I will give you a very nice example. I will give you a very nice example. I think, yeah, let me think about a nice example. Yeah. How about see the example of transients? Maybe let us consider Mr. Jaydev. Okay, so Mr. Jaydev is here, Delhi University, right? Delhi, yes. So he did his BSc in DU. Okay, which part of India? Suppose the map of India is I think almost similar, right? No? Huh? Okay. Suppose this is Delhi. Okay, suppose this is Delhi. Now, let us consider one more. So, is there any? So, when you came from there to here, okay, you made all these new friends, isn't it? Or you already knew about them? No, right? You see, he was not knowing any one of them. No, let us consider Mr. Dikhil. So, Mr. Dikhil. Oh, no, he not here. So, somewhere Delhi is here means Dikhil is here. Kerala. Okay. Now, Dikhil was studying in Kerala, like he was doing his BSc, and Jaydev was doing BSc in Delhi. Okay. So what happened? Like after when they completed their BSc, after some time passed. Okay. How many time passed? Like around 2 years. Around 2 years time passed. Okay. Some time passed. Okay. Then what happened? Nikhil also moved to some place and Jaydev also moved to some place. Okay, what is that place? Yes, they moved to DU. Yes, horticulture. Huh? Attractor. No, not might be. But I'm just telling you the transient. I'm just telling you that. So finally you settled. Finally you settled in DUK, isn't it? Okay, finally you settled in DUK. So what was the transient? The transient was like between the bachelor's and your master's. Okay, finally you converged to your master's degree, like where you two met. Okay, so that's the idea. That's the idea. So you have to discard the transients to consider only the, now do you think about Delhi? Now you think about Delhi. No, because that transient is gone. Okay, transient is gone. Now you are in the original scenario. Okay, so this is a good example of transients. Okay, so something like yeah, like that. Yeah. So this is a good idea why you have to remove transient. Actually, this is a non-linear process. This is a non-linear process, isn't it? How come Dikhil knew that he will meet? How come Jaydev knew that he will meet Dikhil? And did Dikhil knew that he will meet Jaydev? No. Okay, so that's a completely different scenario. So how people meet here? Completely non-linear process. Okay. So this is just an idea of transients to give it to you. Any other ideas of transients you can think of? Any other ideas of transient? Like what you do, you sleep, right? You sleep for 7 hours and you wake up at 6. Okay. You wake up at 6, but your brain is not active. Straightforwardly, do you see a book? No. First thing you see is nowadays is this is it. Okay. So anyway, you see that, but before your brain gets active, it takes some amount of time. So the brain enters to a transient phase till it enters to a steady or stable phase. Till your mind. So sometimes I think you might have experienced that yes, at 8 a.m. actually my mind starts working. Isn't it? Do you think? No, I thought actually. Sometimes I cannot take good decisions when I am just waking away from sleep. Like just 15 minutes after sleep, I might not make good decisions. Okay. So, but after like all my, like I complete my bath and my mind is fresh, I come to like the university and everything, then you see I start making careful and good decisions. That's my perspective I see. Okay. So that is the transient. From the sleeping phase till you come to university is the transient phase. You give enough amount of time for your brain to settle down, start slow, because 7 hours your brain slept, right? You should suddenly not start while starting the bike also. Like, do you start like, no, like, yes, yes. Otherwise, it will put some pressure on your system. So this is just some examples. Uh, yeah. So can we come back? Come back. Come back. So yeah. So can you see this example right here? Can you see this example right here? Okay. So this is the circle map, isn't it? Do you agree with me? This is the circle map. Yeah, just the moment it hit one, it the down again started from here. Agreed? So this is the circle. Okay. Can we calculate the winding number for this? Omega. What is the omega? You did Fn theta minus Fn theta naught minus theta naught divided by n. Limit n tends to infinity, right? What was the circle map here? Theta n plus 1 is theta n plus omega mod 1. Isn't it? So what is omega here? Can you tell me? What is Fn of theta? Fn of theta? No, see, theta 1 is theta naught plus omega, no? Mod 1. Theta 2 is theta 1 plus omega. Theta 1 is theta naught plus omega, right? Plus omega. Mod 1. So this is theta naught plus 2 omega, isn't it? Agree? Did you see this happening? Agreed? So this is for theta 2. If it is so if it should be theta 3, you will straightforwardly see that it is theta naught plus 3 omega. If it is theta n, so it should be theta naught omega. theta naught plus no. Can I use this here? Minus theta naught by n. What this guy should be? Omega. So you can feel now that how much angle it is rotating itself. It is just the rotation number is nothing but the angle by which it is rotating. That is omega. So the winding number for circle map what one do you think? Okay, anyway, doesn't matter. So this is just the winding number. Oh, that if I told you omega can be a fraction, no? Omega can be fraction. Now suppose if omega becomes rational number, then you know that it is a periodic orbit. I told in the previous class. If it is irrational, it should be yes, quasi-periodic. That's it. Okay. So that's what I wanted to tell, because else if I stop it here, then we start from the middle of. Yeah, that is it.